fatty acid synthesis, oxidation, regulation, the very last part of it of regulation, and then moving into amino acid oxidation and production of urea. So you'll notice that, especially in the next slide, in the next section of amino acid oxidation, I've cut out a couple slides. So just, if you have the reader, just go for it, okay? And then I'll post the full lecture. Today I should be able to do it right after. Sorry about Wednesday. I actually had back-to-back meetings and then I forgot. So we'll start right in on fatty acid synthesis and oxidation. So we talked right about how fatty acids are made and then how they are
just two people.
so oxidized. So we're going right into the synthesis regulation right here. So the key enzyme in the synthesis was actually this ACC enzyme, acetyl CoA carboxylase, or ACC. And it can its activity can be modified in a couple ways. And again, these are themes that are coming up, right? So modification can happen by a covalent modification, we're seeing here by phosphorylation. So when it's phosphorylated by pKa, protein kinase A, remember those kinases are transferring the phosphoryl groups. In this case, when it's phosphorylated, it's inactive. And then when it's dephosphorylated, again, phosphatase taking off the phosphate group, it's active. Okay, and again, these are controlled by hormones. So when you have low glucose, right, you have this glucagon hormone going up. If you were to be asked the question, you would know this would be about cyclic AMP levels going up, controlling the pKa activity, which is then phosphorylating to make this inactive. Okay? So when this is inactive, you're not going to be synthesizing fatty acids. You don't want to be using your energy to make fatty acids, right, when you have low glucose. Okay? So when you have high glucose, in this case, right, your insulin levels are going up, they're positively regulating the phosphatase, they're taking that phosphate group off of this enzyme, they're making it active, and it's like, hey, I have enough glucose, I have enough acetyl CoA regulated here, and so I can make fatty acids. Yeah. Better?
Yes.
It doesn't go higher, but sometimes it's my shirt. Is that better? No. Okay.
Gonna have to hold it.
Thank you. Better? Okay. So the other thing is feedback inhibition by palmitoyl-CoA. So we know from making fatty acids, right, that we're actually going to be making palmitoyl-CoA down here in this multi-step, right, conversion where we're adding these sequentially, right, every 2 carbons. And so the palmitoyl-CoA can actually feed back and inhibit this enzyme activity as well. So we have covalent modification by phosphorylation, controlled by hormones, and then we have common theme you're seeing with this regulation of metabolism between all different pathways, and then we also have this feedback inhibition. So what about fatty acid oxidation? So here we go. So now I'm just adding it on. So in this case with fatty acid oxidation, right, in this case with synthesis we have malonyl-CoA, so this is a reminder. So that has to get transported, and that activated, and this malonyl-CoA can be inhibiting fatty acid degradation. So in order for fatty acids to be degraded, the first step is fatty acid CoA going to acetylcarnitine. And so this actually acts to inhibit the first step. So again, this is a really common theme. Here, the first step is right activation, giving this activated malonyl-CoA. It requires energy, and we're regulating it right there at the beginning, so we don't waste the time going through this process if we don't need to. The same thing here, we're actually controlling fatty acid CoA going to fatty acid carnitine, and the malonyl CoA is inhibiting this. And the reason for that is that it's regulating it right at the beginning. So in this case, you're actually regulating it even going in, right, to the matrix of the mitochondria. So you're stopping it from going in, and then you can't actually oxidize the fatty acid. So once the fatty acid enters the mitochondria, it's committed, and so the regulation occurs here, converting it into a form that can actually go in. Okay. So this is another theme we've had about compartmentalization and regulation of that as a mode of controlling whether you're synthesizing or oxidizing. So when you have glucagon, it's also regulating. So here, right, when this was increasing, you were actually inactivating the formation of, sorry, I'm having trouble speaking today. You were inactivating the enzyme, so you were decreasing the synthesis of fatty acids, and at the same time, right, so in this case, when you have low blood, you don't want to make low blood sugar, you don't want to make fatty acids, right? You're in a condition where you actually need resources, you need glucose, you need ATP. So what happens is you actually have the same hormone mobilizing fatty acids to break them down. So it's not only is this hormone controlling this activity here and stopping synthesis, it's also mobilizing, hear me? It's also mobilizing the fatty acids so that they can actually come in, go into a form that can go into the mitochondria, and then be oxidized. So I mentioned that there was product inhibition on the side of synthesis, right, by malonyl CoA. And then again, we also have product inhibition on the other side, and this is all the way down at the bottom. So here, right, we're regulating it. The critical regulatory step is actually converting it into a form that can go into the mitochondrial matrix. And then there's feedback on these two enzymes that's just about the product inhibition. So the ratio of NADH, and if you go back into your earlier notes and look at this process, you'll see NADH is a product, and then here, inhibition by acetyl-CoA, which is a product. So both this is product inhibition.
Professor?
Yes?
I think your mic turned off.
Or you can't hear me? No. It might be this one. It's off.
I think it died.
I might have to scream. Okay, now it's on, right? That is better?
Yeah.
I can't even hear it. It's on, but it's hard.
Too high, right? Okay. Just raise your hands at the back at any point if it goes low, okay? All right. So we just talked about this product inhibition. So we basically had regulation of both sides of synthesis and oxidation by product inhibition, and then by control of that first step into the cycle. And control of the first step was at some level controlled by hormones, whether it's directly on the phosphorylation and activity of the enzyme in fatty acid synthesis, or whether it's also about actually glucagon mobilizing fatty acids to be degraded by beta oxidation. So we talked about fatty acids, and we've been just talking about them in terms of the synthesis and this oxidation. And they have this relationship to triacylglycerols for energy storage, right? So we're not able to readily use, so triacylglycerols is a really good way for storing this energy. The other thing that fatty acids are used for, which we're not going to go into detail, is for the phospholipid components of membranes and also making cholesterol. So this is particularly important under high growth rates, right, where you actually are making lots of new membranes. But here we're just, because of time, focusing on this aspect. So when you form lipids and triacylglycerides, why are we bothering to talk about this? So basically, we have to store potential energy, right, in some form.
Well, that's
And
THG.
so we're only
THG, triacylglycerol.
right? Those are all those glucose molecules. but we're only storing about 100 grams of glycogen in a person that's like a 100 kilogram person. And that would only last for 12 hours. So triacylglycerides fats are actually more important, and basically fats are stored as triacylglycerides. So for a 100 kilogram person, you can have a quarter of that, 25 kilograms of triacylglycerides being stored, and it can actually serve them for 18 weeks. So this could be a huge, really critical source of fuel. Can you hear me in the back? Oh.
You're gonna have to hold it.
I'll try holding it. I'm a little bit like, okay. So if we look at this pathway, we're going from glucose to glycerol 3-phosphate. You'll recognize some of these enzymes. And then we're not going to go through the exact mechanisms. You can look these up, but you can see that you need reducing power and you need ATP. Right, so we're actually making something we're going to store here. We're putting another ATP in, and finally we're getting this as a triacylglycerol. So we know this glycerol structure, right? And then this triacylglycerol can be stored in adipose tissue. So basically in fat cells. So even though you might think you might think fatty acids is what's stored in fat cells, it's actually triacylglycerol is the form that's stored. So I'm not going to be testing you on these exact mechanisms for this formation. I just want you to know that this is the form that it's stored in. And then if we go over to regulation, right, we have dietary carbohydrates going to glucose. Insulin is promoting this uptake by the cell, it's promoting this conversion to acetyl-CoA, and it's promoting this conversion to fatty acids. And then depending upon the levels and the energy needs in all different parts of the body, that can be converted to triacylglycerides. They're also called TAG, and then that's how it's actually stored. So that's how the fatty acids are stored. In a minute, we're going to be talking about amino acids. And so dietary proteins can also be then broken down into amino acids, converted to acetyl-CoA, which could potentially go to fatty acids and triacylglycerols as well. So if we just mentioned insulin here, so if we think about this a little bit more, right, and for type 1 diabetes, you lack insulin production, and so you basically are getting high glucose concentration in the blood and excess glucose in the urine. You're not able to utilize that glucose. So if we look at it here, right, insulin is typically, you have this glucose, but then insulin's promoting uptake to where you need it to convert, and then that conversion to acetyl-CoA and to fatty acids for storage. So if you can't do this, you're really have trouble in terms of actually having the energy reserves you need. And you can see that for this case, right, if you inject insulin, it would solve the problem, right, because it's about controlling this. However, type 2 diabetes is about insulin resistance. So in this case, you produce insulin, but the response is defective. And so the response is about like the receptors, the glucose uptake. So the injections won't help. And so basically diet is the big thing that can help with this. So if the glucose isn't taken up, you can end up, we already know the negative consequences of diabetes in terms of the overproduction of ketone bodies and that kind of thing. But here, where your response is defective, diet is more effective in terms of remedying that. So if we look at this on the next slide, you'll be able to see this. So here, right, we have, in the case of diabetes, right, you have dietary carbohydrates, you have high glucose in the urine, and it goes to the urine because you can't deal with it. So basically what's happening is, right, it's not, so in diabetes, it's not going in and not being converted to acetyl-CoA, not being converted to fatty acids, and not being converted to triacylglycerols. So one of the ways that you can make these things is actually by having triacylglycerols that you can convert to fatty acids to acetyl-CoA, and But you also have a problem because acetyl-CoA can go to ketone bodies and can relate to the pH. So it's a very complicated process, right, how you're dealing with insulin. And in this class, I don't want you to think that we're discussing everything about it. I'm just trying to show you how it relates to glucose regulation at like a simple level. But you can begin, if you're interested, to read more about it, take more classes that get into more details about it. So for this part, we've talked over a couple lectures on fatty acid catabolism or breakdown and fatty acid synthesis and regulation. And the parts that are in gray, you don't have to know because we skipped the glyoxylate cycle in plants. And so I got rid of those here. They're in gray so that you don't get confused because of the difference with the reader. Yeah.
You said the remedy for type 2 diabetes is a change in diet.
Yeah.
And you also mentioned that it has to do with insulin resistance. So what's going on today? We have, like if I had type 2 diabetes, I have insulin, it's just not doing its job properly.
Right.
And so how is changing my diet going to all of a sudden create reduce that resistance?
Yeah, so we don't go into all the mechanisms, that's why I didn't talk about it in detail here, but essentially you're dealing with the fact that you're no longer getting this glucose transported and that you're no longer getting this activated, this acetyl-CoA. So if you change the ratio of what you're eating, and that's actually beyond, I don't want to be giving you those details, but it's the ratio of basically fats and triacylglycerides to things that can totally contain sugar and whatever, and obviously limiting sugar that can impact so that you don't ever have your glucose levels too low here, but that you're providing something that can actually give you the resources that you need to be broken down properly. All right, so we're going to move into amino acid oxidation and production of urea. So I'm trying to orient you in each of these, right? So we just talked about fatty acids. First, we talked about breakdown, going to acetyl-CoA and coming all the way down here to the electron transport chain. And then we actually also talked about its synthesis, but right now we're going to talk about amino acids being oxidized and brought in. So you can see, again, we have to think about where they're oxidized, what they're forming, and how electrons are transported, how it relates to the TCA cycle, and then to electron transport. So whenever we're talking about like beta oxidation and breakdown, we're talking about catabolism in this case. And so generally, this amino acid breakdown to get like acetyl-CoA and generate energy, ATP ultimately, it's done mostly by animals. So like plants, for example, rarely, it's not a major source of their energy. And carnivores, it can be up to 90% of their energy. Herbivores, it's typically less. When does this occur? So it occurs normally, there's always a little bit going on just during the synthesis and degradation of proteins with protein turnover. So this degradation of amino acids is part of what happens with protein turnover. But when you have a diet that's really rich in protein and exceeds your need, you can then also convert that to amino acids, and then those amino acids get catabolized, and we're going to be talking about that. So if you exceed your need, they can't be stored, and so again, they get broken down into ways that you can actually utilize the protein that you ingested. And then also under starvation or this uncontrolled diabetes, you have to use proteins as fuel. So again, in terms of diet, right, you would have more protein. So that's relating to what we just looked at. And so in this case, you have to break down those amino acids to provide the fuel because the glucose part isn't regulated properly. So I added this slide because I think it's actually, when I was preparing, going over it again for lecture, useful prelude, which is that when you have the intracellular protein, you're breaking it down to amino acids. So either from breaking down, and we're going to talk about muscles, right? When you're really using them so much that you actually have to get some energy and glucose coming from protein breakdown, that will be like intracellular protein breakdown and also just part of turnover. But a lot of it for us is also coming from dietary protein. So we have the amino acids, and you know from part one, right, that amino acids always have, right, a nitrogen there. And so this is a really important source of nitrogen for us. And so when that gets broken down, we have the ammonium ion, which I might by mistake just say ammonia. It just depends on the pH status of where it is, whether it's ammonia NH3 or ammonia NH4+. So usually in our context, it will be NH4+. So, and when you break down amino acids, right, there's also the carbon skeleton that we're talking about as well. So we're going to talk about this in two parts. The carbon skeletons can go into the citric acid cycle, right? And then the ammonium, we're going to be talking about the urea cycle, and then these two things are linked. Okay. So before we go into the urea cycle, just for context, animals are getting most of their ammonia, almost all their ammonia, from amino acids and other reduced nitrogen carbon compounds. Whereas bacteria can actually use N2 from the air. So in the atmosphere, so bacteria and some fungi and others can use it. Plants can actually use this form of ammonia, and they use it to make their amino acids, whereas animals break down amino acids to make ammonia. So just to reiterate, animals break down amino acids and other compounds that they ingest to make ammonia, and plants actually use ammonia to make the compounds. Bacteria are really our drivers of what makes this readily available ammonia. And we're not going to go into these, but if you take microbiology, you'll get to go into all these in detail. We're just going to talk briefly here because it's relevant to actually food production and our environment. So biological nitrogen fixation, so converting N2 in the air to ammonia that actually plants can use, is occurring via this enzymatic reaction by the nitrogenase complex. And there are bacteria, right? So the rhizobia bacteria that form nodules on legumes, primarily, that then they do the bacterial fixation of nitrogen, and then they provide it to the plant, and the plant provides the rhizobia with carbon. So this is actually absolutely critical. And people also use sometimes, like in organic farms, and also sometimes others, they'll use a winter crop. So actually in an organic farm of a friend of mine in Bolinas, they have a legume crop that they'll use in between their other crops, and so then at the end they'll have this fixed nitrogen that's in that leaf mass, and then they'll just let that degrade and go into the soil and be available. So this is very important. There are also researchers that have been looking at how we can actually expand the range of plants that are able to host these rhizobia and form nodules to get more nitrogen from N2, from available atmospheric nitrogen. So most of the world is actually using fertilizer for plants, for all the plants, most of the crop plants that actually are not able to form these symbiosis. And so this is the process that's used. And just to appreciate for the chemists in the audience, in making this chemically, you actually have to go to 400 to 500 degrees Celsius and 300 PSI. I mean, it's just incredible the amount of energy that goes into this. So 2% of the world's energy supply is going into making fertilizer. So, and yet plants can do it, right? They're using a lot of ATP, but plants in association with the bacteria that can do this. So expanding this knowledge would be really important. Oh, and then previously, before people could do this reaction, they would actually go around and harvest bird shit, basically. Yeah, so they would, and really rich in amino acids, and so that's actually what would be used as fertilizer. We also know excrement from other organisms too, right? When people are going and getting also like manure from other sources and putting it in your garden, when you're selling that, that's what they're doing, right? They're making availability of all, you'll see in a minute, from the recycle, all of the stuff that's secreted. So what about humans and nitrogen? So this is the pathway that we're looking at, and we're basically going to start, I'm just going to go over here. So you have, you start in the gastric glands of the stomach, and basically what happens is they secrete HCl, and so then this HCl converts. So now we have a new theme that I'll ask you in a minute if you talked about in the first part of the class, but this new theme is, we've talked about how do you control an enzyme and its activity. So the new theme is you can have a precursor form of the enzyme, and under different pH, in this case it cleaves, and then you get the active form of the enzyme. Did anyone talk about that in the first part of the course? Yay, okay. And then the other thing that can happen is, and both we're going to talk about right here, right now in this slide, is you can have a precursor form of the enzyme, and then only in the compartment where you have an enzyme that cleaves it do you get the active form. So there are a couple ways to regulate that. So this is this precursor type of regulation. So in this case, when you have the low pH, which is secreted here, you actually convert this proenzyme and pepsinogen into active pepsin by this pH-dependent cleavage. And then you have this pH-dependent cleavage. First of all, these were just really general things about the low pH here in the stomach. So basically, you also have protein unfolding, which allows for easier digestion by the enzymes and accessibility, and you also get killing of bacteria. So from there, what happens is you have that low pH, you have the pepsinogen going to pepsin, the active form, which was cleaved, and then you get this secretion of secretin into the blood, which is a hormone, and then it's telling the pancreas signaling the pancreas to produce bicarbonate, and then the bicarbonate is released in here, and now it brings the pH up from like very low, like around 2 to 7. So it neutralizes the acidity here in the small intestine. And then in the small intestine, you have these ducts that have these granules associated with them, and they're using the word zymogen for the precursor of these particular proteins. So the zymogen so basically it's this form that's not active, then they basically get converted through an enzyme that's only released here in the pancreas to their active form. So these enzymes are trypsin, chymotrypsin, and carboxypeptidase. So they're just cleaving off different residues and different types of bonds in proteins to degrade them. We're not going into the details of that in this part of the class. So you have the active form of it, and then you have that degradation. And then from there, right, you have those amino acids, they then they get absorbed back in, they can go to the blood and then to the liver. So in the liver, so now we're starting with amino acid. Okay, so we just broke down the protein into amino acid. It went into the blood, and now it's going to the liver. So in the liver, we have the amino acid, and what you're going to learn over the next couple of slides and from your book is that there are a couple key amino acids that are storage forms and are transported for nitrogen. So an important one is glutamate. So in this case, glutamate is not transported, but it's a pool where all these different amino acids through this reaction, which you want to be familiar with, can transfer the ammonia group to glutamate, okay? So all the different amino acids can come in and they get transferred to this one product, and then that can feed into the next reaction. In the meantime, you're not losing any ammonia group, right? You're transferring it from here to here, so they're all in the same compound, and then the alpha-ketoglutarate is going to a keto acid. There's a cofactor that we're not going to talk about in detail, I always have trouble saying it, pyridoxal phosphate, and that's facilitating this reaction, particularly with the nitrogen, the amino transfer. But again, I just wanted you to know the cofactors there. So here, right, you've made the glutamate, but then you have to bring this into the liver and into a form that's useful. So it's in the liver. Sorry, I might have said bring into the liver. So it's in the liver here, and then what you're doing is you're converting it to be able to use it. So you have the glutamate going through an intermediate and releasing alpha-ketoglutarate and this NH4. So it might look, so the whole key about this is if you already have glutamate, you just go to the next step, but if you have any other amino acid, you're going to glutamate, then they can all go through this process, okay? So glutamate is then going into alpha-ketoglutarate and releasing ammonia. So there'll be two parts we'll talk about, right? What happens with the alpha-ketoglutarate? Well, we know this molecule from the TCA cycle, so it can go right in. And then what about this product, this ammonia? Well, this is toxic, and it also could be useful depending on our needs in the body. So we want to capture this for transport, but we want to have it in a way that's not toxic. So how do we transport this? So for example, if you're in the brain or most tissue, what happens is, so the brain releases amino acid and this NH3 or NH4 plus, and so you have it as glutamate, which we talked about, and so then what's happening here is it's getting converted to glutamine, and this conversion to glutamine, right? So here, this NH4 plus is toxic. So we just talked about it here. We had glutamate to alpha-ketoglutarate. We've done this, but now this is toxic. So then what do? We have glutamate plus the NH4, and we convert it into L-glutamine. And this is the big transported molecule. So now you have two nitrogen groups that are being transported around. And this is non-toxic and transportable, as opposed to the ammonia. So this can then be moved through the bloodstream to different locations. And what you're seeing here is now it's going to the liver, then we're actually taking off the NH4 again to make glutamate. So again, you're seeing a lot of cases, right, where you have an interconversion. You have something, you go to something else, you bring it back to that same thing. It's like, why? This is a lot of work, but it has to do a lot of it with transport. Right, so we have to be able to transport it, and we can't transport that ammonium in this way, and so we're actually putting it onto glutamate to make glutamine, and now we can transport it, cleave it off, and here in the liver, we can convert that to urea. So if it's coming from the brain, it's coming from anywhere else except for the liver, right, we need to actually get it into the liver to be able to make urea. So muscle can also use a different way, and often it's the primary thing that it does. So for muscle cells, you actually can transport with alanine. So we have two transporting molecules. We have glutamine and we have alanine. And the reason that alanine can be used is because of what's going on in the muscle. So when you're actively exercising, you actually could start degrading muscle protein to amino acids. Every time when you're degrading that, you're releasing, right, in that very first step, that ammonia group and the glutamate. So in this case, right, the glutamate gets converted here to alpha-ketoglutarate in the muscle, and that is coupled to conversion of pyruvate to alanine. The alanine is non-toxic, can be transported in the blood, it gets converted back. Right, the same theme of like you make something, you transport it, yet you make it back to what it was, and then the alanine goes back to pyruvate, and then you can make glucose. So what you're doing is you're really coupling this amino acid catabolism with the generation of pyruvate, and then you can keep making more sugar, which is what is needed, right, when you're actively exercising. And the other thing is, if you end up being in an anaerobic situation, right, this can actually be very important in terms of a way to make glucose. So to summarize what we just talked about here, basically you can have amino acids that are ingested from protein, and then this aminotransferase, where in the liver, can go to alpha keto acids and, where's the ammonia? Here, and glutamate. Okay. So we know this alpha ketoglutoacid glutarate can go to TCA cycle and glutaneogenesis. So if we go back and look at the TCA cycle, we can review that. And then also, we, from here, right, have the ammonium stored in the glutamate. So now we're going to follow the ammonium right here. And then that gets converted to alpha ketoglutarate and released as ammonia here, which can be secreted by making urea, which we'll talk about in a minute. And then if it needs to be transported, what's happening? So this is if it's in the liver, right? No transport necessary. If it's in the brain or somewhere else, you get the glutamine. So you get whatever amino acid, it's converted to glutamate. The glutamate is converted to glutamine. The glutaminase then converts it back, to glutamate. Sorry, the glutaminase, you bring it in, and it converts it back to glutamate to releasing the ammonia for secretion and making it basically urea. If it's coming from muscle, it's coming in as alanine, and then that alanine again can feed in here in the liver. So the major point of this is that if you're in the liver, you can directly, right, release the ammonia, and then you can make urea and get rid of that toxic ammonia. If you're somewhere else, if you're in the muscle cells, you can do make alanine, and then that gets transported and then basically converted back so it can go into this cycle. And if you're in the brain or other tissues, not the liver, you can actually transport it as glutamine. It gets converted back to glutamate, and then you have that ammonia for secretion. So the transported amino acids, like I've been emphasizing, are alanine from muscle and then glutamine from the brain. So we now have this question with your eye clickers.
Alanine. Right? Oh, or it's that. Isn't it? Alanine, right? Alanine. Alright, cool. Oh, hold up.
Wait, which one are you picking? Alanine or glutamine?
Alanine. Alanine, right? Yeah. Because that's the one that enters in.
Yeah, blood alanine. Blood glucose goes in.
No, when you're working out.
Yeah.
In blood, yeah.
After, and then it goes back to glucose. I wish the exam question with this is easy, you know? Or not easy, but just like lovely.
Okay, so if you haven't answered, you want to answer now. 5, 4, 3, 2, 1. Okay, so we're going to stop this.
Now there's 300 people already.
Sorry.
Everybody click A. There's how many people?
300. Just in class today, but like I'm pretty sure like 400 and
Okay, so what I figured out is it actually depends on the order of which I open up the clicker versus PowerPoint when I can't get to it again. So I apologize for that, but there may have been a couple people who then got the right answer but that didn't, but I think you probably all already had it. So let's look at that.
It's a she don't get it.
Yay!
Uh-huh.
So we had just
More
talked about
people.
it, but
Five,
when
6.
you're reviewing for the test, right, you want to go through and think about the
CD.
details of why, because we move through everything so quickly as we're forced to in lecture.
I didn't read the answer.
We didn't read the question.
Are we done?
All right, so almost everyone got this right with alanine. So we still have 8 minutes, and we want to talk about the next part, which is actually what happens. I kept talking about urea and the uric acid cycle, but we didn't go into it yet. So we're really focusing right here on urea, and you can see that, right, it has 2 nitrogens. And for most terrestrial animals, this is what the most important thing is. So this is toxic, and this is what's formed actually in order to secrete, okay, and a non-toxic product. Don't worry about these, I was just showing you that they're made in different types of organisms. So the urea acid cycle is actually, again, a cycle. And so you have 2 places where ammonia comes in. It comes in here with CO2 to make citrulline. So these 2 are amino acid type structures, but they're not found in proteins. And ammonia also comes in here to make arginine. And for this, you need to know the cycle of it, but not the actual detailed reactions, except we're going to talk a little bit about like if energy comes in the next slide. So the main part here is that you're taking ammonia and you're getting rid of it because it's toxic in the blood and you need to do something with it, and the liver can deal with this. So you've transported it to the liver in a form that was transportable, and now it's like, okay, we have to deal with this, we're gonna make urea. So it's made in the liver, and then urea goes to the blood, to the kidney, and then out through urine, right, as one of the forms that goes out. Krebs was one of the discoverers of this cycle, along with the Krebs cycle. So if we look at this pathway, the major part that I want to emphasize here, you don't need to know all these structures, right? So we're going to just start with, right, so here we have the ammonia coming in here, and then we have the ammonium coming in here on aspartate, right? So in this case, we have the ammonia coming in. So this is really the major ammonia that we've been talking about. So the ammonia is coming in that we want to get rid of. We're using ATP to do that. And this is a like highly regulated enzyme, the first step, of course, right? This is a theme. So now we're going from the mitochondrial complex into the cytosol, where we're having the urea cycle happen, and we get this conversion to these unusual amino acids. And finally, if you were to look at this product, like this reaction, right, you'd see urea as a product, and you would see fumarate as a product. And you should recognize fumarate, right, from the TCA cycle. So there are 2 parts here that are obvious linkages to the TCA cycle. There's the production of fumarate, and then there's the actually coming in of bicarbonate, which is actually coming from the TCA cycle. So if we look at this on this slide, what I'm stressing here is the connection between the cycles and how we get rid of ammonia and how we actually move carbon. So here we were talking about the urea cycle, right, where we have bicarbonate coming in and ammonia coming in, and then that is released as urea, which can be secreted. But at the same time, right, we're forming fumarate. So whenever you have two things coming together, right, this is a conversion here, where aspartate goes to arginine, and then we have fumarate formed, okay? So fumarate's formed, and right here, it gets converted. So again, this is about compartmentation. So here we're in the cytosol, but we know the citric acid cycle is here in the matrix. So we formed fumarate, but we need to get it into the citric acid cycle. There's a trick, so I do want you to be able to think about this trick. It can't just go in as fumarate, because there's no fumarate transporter. So what do? We go to our old friend malate. The same thing here with why aspartate's used here, right? Because this is a malate aspartate shuttle. So aspartate's going out, malate's coming in, and then that can feed into the TCA cycle. Okay. So if you were to look at the energy requirements, it would be ammonia, CO2, aspartate, and ATP. And then that would be forming urea, fumarate, and then this conversion of ATP to ADP. And then you're also getting products for high energy phosphate groups. What I want to focus on here is just having you look at the reaction and see these components coming in. So again, you have your ammonia coming in, you have your CO2 coming in, right? And then your aspartate as something that can easily be transported and used here. And then ATP was coming in at different parts of this cycle. The ATP is from 2 ATP here and 1 ATP here. So the last part that we're going to talk about today is the regulation. So we have the urea cycle. If you have a high protein diet, you would have a lot of these carbon skeletons, a lot of, basically you're having amino acids being broken down, you have a lot of carbon, and you have a lot of ammonia you have to deal with, and so you get this urea production. And then the same thing so this is basically you just have too much protein, you can't actually utilize it, we can't store amino acids, and so it has to get processed, they get broken down, and then the nitrogen part of it gets released as urea. And then also under starvation conditions where the only source, or like this rapid exercising, right? In order to have enough energy, ATP from muscle contraction, you start breaking down your muscle protein, and then that muscle protein is actually as part of amino acid catabolism, you're releasing ammonia, and then you have to get rid of it, and it's getting rid of as urea. So what happens in terms of the regulation is that under these conditions, you have higher expression of the enzymes, so there's transcriptional regulation, and then there's also allosteric regulation where we enter, okay? So if we look back here for the urea cycle, there were 5 enzymes that were involved, and so all of those get upregulated, and then this is that entry point, the carbyl phosphate synthetase 1, and this is highly regulated. So again, another theme, it's usually about entry. So here, we have regulation by amino acids are positively regulating this, and then we also have a requirement for ATP. So the major things here are actually an allosteric regulation of this, and also requirement for ATP. So you have synthesis and you have allosteric modulation. Thank you.